Inspired by the findings in my previous video, nerds111, I am starting a new project using here 21 crystals in a proper crystal oven. A big chunk of copper where the crystals are pressed in slits with press fit. So the thermal contact is very good between crystals and copper. Normally there would be a copper lid and some thermal isolation on top. The white stuff you see closest to the copper is an aluminium silicate that has a very good thermal isolation property, and it can stand over 1000 degrees. And then there is some plastic. I don't know exactly where it fails, but certainly if I put it in boiling water it will collapse. But at the normal operating temperature it doesn't collapse very quickly. So I guess this will work for in the long time scale. And then I have just capacitors and a coil or two to measure the basic performance of this unit. What you see here, the copper, this is for measurement of the crystal current. So I can put the current probe like this, and it doesn't affect Q very much, or rather very little. I can also measure what happens using an oscilloscope probe directly on the crystals, which will be here. Here is the schematic diagram. The coupling capacitor is 27 pF, and the tuning here is 250 pF, 100 and 150 in parallel. The Q I find is 1.086 million at a frequency 15 Hz above 10 MHz, and the loss is 27.39 dB. There are many turns here and few turns here, but it's coupled through 4.7 pF, so this doesn't load significantly. Maybe 2 or 3 digits on this position. Anyway, it's constant with these experiments. When I put the current probe on its position, I see 60 milliamps peak to peak when I feed 13 dBm into this point. And when I look with the network analyzer, I find Q has dropped from 0.086 to 0.070, frequency unchanged, but the loss has increased by 16 decibels, 0.16 decibels, sorry. And when I put the voltage probe on the crystal here and remove the current probe, then the Q drops significantly more to 1.059. It is still not a big change. The frequency has dropped by 2 Hz and the loss has increased by nearly 1 decibel, 0.8 or something like that. You can calculate yourself. My head doesn't do this automatically anymore. The voltage probe gives me 2.20 volts peak to peak, and I want more to have a good low noise at wide offsets. The flat noise floor goes down when I have a larger voltage here. The current is 60 milliamps peak to peak. That gives 1.01 milliamp RMS for each crystal, and that gives me 71 microwatts per crystal. So this would be a suitable operating situation. 13 dBm at this point. I don't know the maximum for these crystals, but I have similar crystals that are rated 100 microwatts. The next step is to make an up transformation with this transformer, and I want the impedance at this point, measured with the transformer only, to be much higher than 700 ohms, which is the impedance at this point when there is nothing connected here. This is material 61, 2 plus 6 turns. This is what it looks like. It's a bit inductive. I can remove that by changing the electrical delay. Scale, electrical. And here it looks like 2 kilo ohms. And it is better seen in the impedance magnitude format. Here you can see the optimum. I fine-tuned the electrical delay. So I see 2.1 kilo ohms for the 61 material. This is material 65, 3 plus 9 turns. It is even a little more inductive, and I go for the electrical delay to tune out the imaginary part, the other direction, here. It looks like 2.5 kilo, and again I look at the impedance magnitude and then tune the electrical delay, and I can see this is significantly better. It is about 5 kilo ohms, and since the impedance level coming out from the crystal is 700 ohms, this would not degrade very much. 5 kilo ohms load on a 700 ohm source. This is material 67, 4 turns plus 12 turns, with a significantly thinner wire. This is wire wrap wire. And I'm still in the impedance magnitude mode, electrical delay. Here I have to change scale, 2000 ohms, 5000 ohms. So this has a very high Q and will not load at all, although it is a reactance. If I look at the Smith chart, well, first electrical delay 0 milliseconds and format Smith. So you can see it's 12 microhenries. But since Q is very good, this will just move the frequency a little bit. So this one is a good alternative. This is a quadrifilar winding on a T50 core of material 2. It is about 6 kilo ohms, and that is with electrical delay 0, because one can tweak the winding to tune it to the correct frequency. But losses are much higher than with the 67 core. I am testing the first amplifier stage, the source follower with 3 JFETs, J310. So I just connect the drain to 16 volts, that's the plus line there, and put a transformer, 12 turns and 4 turns. That's the same transformation as here, but in the other direction. The output impedance here is very close to 0, so I have to add 47 ohms and 1 nanofarad to get 50 ohm to send to the phase noise analyzer. The very first test is with the box open. I have not made a lid for it yet. And here is the result. There is some fairly strong noise here, but in absolute numbers, minus 140 dBc per hertz at 10 hertz offset is not bad. And the flat noise floor looks good. Now there is a lid on the box. Here is what I see after about 2.5 hours. I cannot see the noise from 1 megahertz down to about 50 hertz offset. You can see the circles all the way. It means it hasn't converged yet. Then I see a clear noise signal generated by my selective amplifier. This is the gate to drain capacitance variations that frequency modulate the crystal. And this is what I can remove by applying a voltage on the drain that follows the gate. I think it's called bootstrap, I'm not sure. And then from 1 hertz and closer to the carrier, I cannot see the noise either. Here there are only circles everywhere. I can compare this with a graph from the previous video, nerds111. It's here. This is 25 hours, 10 times longer. And here I can see noise in this region, around 100 hertz, here. And now the noise is lower at this offset. And that's interesting. And what will happen here, I cannot say, but I couldn't see the noise after 25 hours previously, so I guess it is the same. Anyway, this has been successful. I don't see anything undesired. So I will continue adding the amplifier stage required to try to remove this. I have added a second amplifier stage like this, with 4 transistors in parallel. The tuning of the entire system is like this. Step 1, disconnect here and send 13 dBm into the unit, and then set the current to 60 milliamps peak to peak as measured in this wire. Then the voltage measured at this point is 2.2 volts peak to peak. And this capacitor is set to obtain these currents and voltages at the frequency of my Wenzel oscillator, which is 17 Hz above 10 MHz. That's step 1. Step 2 is to disconnect at this point and also at that point, and measure the impedance at the peak of this parallel resonator and tune it to the frequency we want, 10 MHz. Then connect this link and connect here to ground and tune this one for a minimum impedance as measured here. That should ensure that there will be a 0 phase shift from here to here. And then, before doing that, when this is disconnected, tune this inductor for the same voltage, 2.2 volts here. Means we want to have the source loaded with something that is not reactive, neither inductive nor capacitive. And then when we connect this, we shouldn't change the reactive component. And one more thing, feeding a small signal into here, tuning this one for resonance at the drain when this capacitor is disconnected. We want to balance this 100 pF capacitor, which is needed to avoid self-oscillations here. And we don't want to load the signal fed back to the drain with some big capacitance here. So this is to cancel that. Then I have not tried to optimize the similarity between this voltage here and the gate voltage. I just say, well, this should have unity gain, which of course there is a small voltage drop here, and there is a small voltage drop here. So the amplitudes are not perfectly equal. And there could be a little phase shift also, and I have not tried to get rid of that. And then this amplifier must not be loaded, because if I load it, the voltage goes down and the difference from here to here becomes greater. So I take the output from just 3 turns where the primary windings, they are equal because this is a bifilar winding, 11 turns, and here only 3 turns to make my test system load this stage with 4 transistors very little. So the basic idea is that with having several transistors in parallel, the output impedance becomes very low, so this circuit should not load much. This 22 ohm resistor should give a very small voltage loss because the impedance would be high on these FETs. But this resistor is necessary to avoid self-oscillations at VHF in this transistor, which has some coupling between source and drain. If I would connect directly without this 22 ohm resistor, this capacitor has a series resonance at about 80 megahertz, and that causes self-oscillations here. So this must be prevented somehow. I realize I made a drawing error. I had drawn a wire from here to here, and that's incorrect. It should go to the bottom of the coil, which is decoupled for RF. Otherwise, there would be no biasing on the gate. This has been running for about 10 hours now. I can compare it with the graph from the previous video, nerds111. Is here. This is 25 hours. And there are 2 major differences. Firstly, this structure is pretty strong. I think that is because the voltage on the gate and on the drain of the input source follower is not equal. So the random variations of the gate to drain capacitance creates this noise. Look at the previous video for details. I think it will be possible to tune this away, at least to a fairly good degree. The other difference is here, down around 100 Hz to 1 kHz. This looks like flicker noise in the amplifier stages. That should be slope 1, like this. That's down here. And then there comes a contribution from this, and maybe some other noise also. So now it is much better. You can see it has not converged yet. There are circles everywhere. So this looks like it is almost flat down here. And in the nerds111 there were 2 amplifier stages. Now there is only 1. And I don't want to wait anymore for this, because I will look at the possibilities to tune out this. I cut the wire here and introduce through a 680 ohm resistor and another capacitor a signal to this point without disturbing the DC level. And I set the signal to get nearly 2 volts here. I cannot get quite as far, but it's near. This means that I feed this transformer from nearly 700 ohms, 50 ohms from the signal generator plus 680. And I know that the impedance in this point is 700 ohms. I look at the same signal with 2 probes for the 2 channels of the oscilloscope. And channel 1, like that, they are very similar. But I want to do this very accurately, so I increase sensitivity a bit and then add and invert. And here is the difference. And I can tweak the gain knobs. And here is the minimum. There is a phase shift between the probes. And there is a variable capacitor here. So I have tweaked it, and now the difference between the 2 traces are very close to 0. So now I can look at 2 different signals. As it turns out, when I put one of the probes on the gate, it loads so much that it's hard to see the difference. I can see it is there, and I can see that the signal on the gate is a little bit stronger than the signal on the drain. I have to balance the probes at a lower signal level. Now I have one channel 1 on the top trace, and when I move it you can see we have non-linearities in the oscilloscope, and it's the same for channel 2. So I need these signal levels when I do the experiment trying to make gate and drain voltages the same. The first time mark is the drain. I can disconnect it. And now I will make add and invert. And here we can see that it is negative for the drain. So the drain is a little bit weaker, but the phase angle seems to be very good. I have added 1 turn, and this made the voltage equal, but I can see some noise. There is amplitude noise between the 2 measuring points. The track is going up and down. Very little, but it is clearly seen. Maybe if I move the trace a little bit. You can see it here, I think. I don't know whether this is the oscilloscope or whether it is my oscillator or amplifier. It's not an oscillator yet. To find out, I look at the same signal with both probes. And this is different. I see jumps now and then, as I did before, but that continuous small noise is no longer present. So it is a phenomenon in the amplifier. I don't know the reason for it, but I guess it's flicker noise that changes the amplification. I have added 1 turn here, to increase this voltage by about 10%. And that makes the voltage, the AC component of it, equal between drain and gate. Now, not under normal operating circumstances, because I have loaded the gate. I don't know whether that matters or not. This has been running for 16 hours now, and it is with that extra turn added. What I had before is this. So it seems I have lost something like 6 decibels at 10 Hz offset. And this doesn't really make sense, because when I started the measurement it looked like it was better than before. So I will restart to see whether there is something that happens suddenly. Well, obviously something has changed. It is even worse now. Here is what I had over 16 hours, and this is after a couple of minutes only. And you can see it's really bad. So I have to open the box and see if I can find what has gone wrong. I have restored this configuration on the source side. Just a transformer and then the output after some down transformation. The same transformer as I used quite early in this video. But I have not changed anything on the gate side. So there is a capacitor here, and there is more capacitance here than it was when I did this. The frequency has gone down now by 13.9 Hz, 14 Hz, so it's far from the correct frequency for the vent cell. I am using the network analyzer and stopped it on the peak so I can see where the frequency is. So I have to change on the gate side quite a lot. 14 Hertz for removing that cancellation of the gate to drain capacitance. It's a little bit larger than I expected, actually. I have left this 4.7 pF in place, and then I had to reduce this capacitor by 100 pF to compensate for the removal of the gate to drain capacitance. That's because the up transformation here is larger now than it was in the previous video. So maybe there is a problem with this capacitor. I will soon see. This does not look right. Maybe something has moved inside the box. It is mechanically very poorly designed now with that transformer hanging in the air. I will restart to see whether it happens again, this feature, which I have difficulties to understand. What I saw in the beginning of this video here, it differs a little, but here it differs in the other direction. So I restart it. Now this looks better. The problems here have disappeared. If I compare with the results from the start of this video, here you can see here is a significant difference. The number of averages is 163 and 202, so it doesn't differ so much. So there is a loss in performance at 1 Hz, but at higher offsets the difference is much smaller. Or maybe there is no difference. I restart this again because now it's late in the night and I'm going to sleep. So we will see tomorrow if it is different or not. So I stop and start. Now this looks better. The problems here have disappeared. If I compare with the results from the start of this video, here you can see here is a significant difference. The number of averages is 163 and 202, so it doesn't differ so much. So there is a loss in performance at 1 Hz, but at higher offsets the difference is much smaller. Or maybe there is no difference. I restart this again because now it's late in the night and I'm going to sleep. So we will see tomorrow if it is different or not. So I stop and start. Here is what I collected during the night. Not particularly good. I restarted, and here is what I see now, even worse. So something is changing. Maybe I could wait for it to fail completely to make it easier to find. I don't know. I have cleaned the BNC connectors. That seems to have fixed the latest instability. This was what I had during the night, and this is what I have now in a very short time. I will wait for a while to see if this is restored in full detail. There is a new problem. It looks like the gate-to-drain capacitance, this curve from here, but it is something else. I made a time-lapse video how it builds up. It goes fairly rapidly. Here is the time-lapse video. You can see here it jumps up again. So it is not a constant thing. It's a little bit unstable. Contrary to what the gate-to-drain diode is. And I don't remember how long time this was, but it is 10 seconds per frame, so it is not many minutes. I have opened the box and I will start a new recording with the box open. I have removed almost everything, so what you have seen is just the source follower. And there is no biasing, this is grounded here. So I want to avoid everything that could cause noise. And still I see this problem. Since there is no up transformation, the noise of the gate-to-drain capacitance is far less insignificant for the frequency variations. That's why I say this doesn't come from this capacitance. And with the box open, as is now, it looks fairly similar. I don't see much interference picked up. At this point, I would suspect the crystals. So I open the thermostat. It is this plastic, and then there is this aluminium silicate. I have to be careful because it's very brittle. Like that. And I unscrew the lid, 4 screws here, and open the thermostat. And here are the crystals. I have disconnected one of the groups of crystals here. When I disconnected one group, I had to change the capacitors down here, of course, to move them to have the resonance on the right place. Here it looks fine, as you can see. It is one row of crystals disconnected. But I have done this once before. That's why I'm making a recording of it. And that time I tried 2 halves of that disconnected, and they were both okay. And then I connected back everything, and it was okay for some time, and then I had the problem again. So now I will leave this running for a long time to see if something bad comes back. This is 5 hours with 14 crystals, and the result is very peculiar, I think. I have made a time-lapse recording during these 5 hours, and I will have a look at it. This is the time-lapse video. And here I'm starting, and I move 1 frame at a time forward. And you see there is no problem here. And I allow it to run at normal speed. And something starts to grow here. And at 1 hertz it looks like minus 130, which is quite good. This suddenly becomes much stronger. But it stays within this range. And here it looks like better than minus 130. And now something happens. A peculiar phenomenon. I don't know what it is. Maybe it is parametric oscillations somewhere. I find it difficult to believe that crystals could have such phenomena, so it could be the transistor. It has a capacitance diode, or 2 of them, and that could cause oscillations, perhaps. Well, that was all of it. I can start evaluation right now to see this is real time. Well, I have this problem here, but it's not so strong as it was towards the end of the time-lapse recording. By holding the tip of a pencil like this, on the 3 electrodes, one at a time, on the FET, I could load with a lossy capacitor, and I didn't see any change at all of that little peak, which was fairly stable when I did this. So I concluded, no, it cannot be the transistor, it must be the crystals. Here is the current through the crystals. It's about 47 milliamps peak to peak, and that becomes 1.2 milliamp RMS per crystal for 14 crystals. That is about 90 microwatts per crystal and shouldn't be too much. But there is one interesting thing. If I put a screwdriver here on the unused crystals, here, look at what happens on the oscilloscope. These crystals are capacitors, but they are also mechanical resonators, and they should have a resonance frequency significantly above, because the capacitance is only the capacitance they have on each others, and there should be about 100 pf to make them resonate at the frequency where I have the signal. So I will short the crystals, and now I start again to see whether that problem has disappeared or not. Well, seems promising, but I will wait a couple of hours because it has been a little bit sporadic and maybe it will come back, maybe not. This is 5 hours with 14 crystals, and it is still the single transistor with no transformer and no biasing. And what I can see at 1 Hertz, maybe 134 or so. It has not converged yet. There are circles around here. The signal level is low because there isn't any gain. But as a whole, there's nothing wrong with these crystals. I will connect 4 of the 7 ones not used to see whether they also are okay. This is 18 crystals, with 3 of them shorted. And I have this interference that I was starting to look for. So 1 of these 4 is not okay, or maybe more than 1. So I will change the configuration of crystals again. This is not good. I must conclude that one or the other of these 2 crystals is noisy, because these 2 and these are grounded. So one of these 2. I disconnect one of them and retune. And I do not forget to short the other one. This looks okay, although statistics is not very good yet. So I know which crystal to replace. This is the bad crystal, and here is the Smith chart for it at the power level of -20 dBm. I will replace it by this one, and they look very similar at this power level. I have saved the other one so I can compare them. This is data and memory. Here is the one I want to replace it with, and here is the bad one. And I can look at a different format. Impedance magnitude. This is the one I want to replace it with, and memory, that's the bad one. And you can see the frequency differs a little bit, but at the thermostat temperature it should differ very little. So far I don't see anything of interest. Instabilities have come back. I'm replacing all of the crystals, and this time I will limit the power to 10 microwatts per crystal. The crystals I have used were from this group with resonance frequencies from 9.940 to 9.943 MHz at about 78 degrees. And this is the new ones I will use. They are about 5 Hz higher. And I have 26 of them, and I had 31 here. So maybe by looking at them one by one, I could find which ones are not good anymore. But that will take a lot of time, and it will be easier just to put new ones there and hope for a better luck this time. Here is the result for the new set of crystals. This is at 10 microwatts for each crystal, and performance is really poor. I have increased the level by 5 decibels for 30 microwatts, and this is much worse. Here is what I had with 10 microwatts. It seems it is necessary to test the crystals one by one. This is 3 microwatts per crystal. And here is what I saw with 10 microwatts. Noise in crystals is nothing new to me. It was a major problem when I started this series of videos for nerds. To find what I did initially, go to my homepage, sm5bsz.com, scroll down until you find lean rod, click on that, and then you can see here are videos showing installation, calibration and usage. Click on that, and then other videos or sideband noise for nerds only. And here you can find noise in quartz crystals, several videos. You can see all the way here. The problems I had were with computer grade crystals. They're very cheap, and it's not surprising that there are quality problems with them. They're not intended for low noise oscillators. But I thought that these third overtone crystals would not have noise problems, and the conclusion I could draw when putting 20 of them in a box was that this was a good assumption. But now I know better. I have to check them all one by one. So I will show a little bit what I found in earlier videos, and then I will finish this video and make a new one on noise in quartz crystals of the third overtone type that cost about a factor 100 more than a computer grade crystal, which is on the fundamental, while these ones are at the third overtone. Here is nerds2. I start playing it at 21 minutes and 30 seconds.
And I have these parasitic oscillations from crystals somewhere. And also on the low side.
You can see the noise.
I think they are
here
due to mixing. There is the strong carrier, and this spur mixes and comes up here. And I think that mixing is done in the crystals.
In Nerds 47, I look at individual crystals with interferometry. I start playing at 33 minutes.
And what I see now is pretty ugly. The crystal has all sorts of oscillations on the sides of the main signal because the power is too high. There are interesting patterns. This spur that comes from the crystal goes up and down in a funny way. Here I have run at different power levels. So this is with a 3 dB setting on the attenuator, the maximum power that the crystal should accept. And here is 3 dB more attenuation, and we can still see an elevated noise floor. So 6, 9, 12 dB. At this point there are some odd phenomena close to the carrier. And then 15 dB, 18 dB. Here it looks pure, but the carrier is 18 dB weaker. So we make an oscillator, this is not very good. So I will measure performance of, I will look at a couple of other crystals before deciding how to proceed.
So there are problems, real problems with these computer-grade crystals. And these crystals are very different. I play a little bit more.
Here is another crystal, my number 161. It is more noisy and it has these ugly sidebands that travel up and down, as you can see. There is also, at an offset of 100 Hertz, a very narrow spur. This is because of my local magnetic fields. It's the overtone of 50 Hertz.
Here is another sequence.
And I lowered the power on it. And here is what it looks like. The attenuator setting 3 dB, 6, 9, 12, 15 and 18.
I found significant differences in the noise level at 25 Hz offset, from minus 153.9 to minus 135.7. That is a very big difference, and this was just a couple of crystals. This is from nerds112. I found that the noise as dBc per Hertz does not necessarily increase with power. It can also decrease. This one, for example, at minus 16 dBm power developed in the crystal, it is specified 0 dBm. At more power, it is better, and even better.
I have tested all the crystals at 3 different power levels. Minus 16 dBm power dissipated in the crystal and the corresponding attenuator setting, up to minus 4 dBm. And here are the dBc per Hertz levels observed. And then I have sorted in order of increasing power from minus 168, and the worst one among those that I have classified as good was minus 133. So that's more than 30 dB difference.
Another sequence from nerds112.
Attenuator. And here is 3 dB less power than the level I had here. So here is 6 dB, 3 dB and 0. So this is a phenomenon that happens at a particular power level. I will not use this crystal.
I will try to find a good way of measuring the noise produced by these high Q third overtone crystals. That will be the next video, nerds113. And this one stops here.